Hello and welcome back. So in our previous segment we were talking about what was meant by valence electrons. So valence electrons are going to be the outermost electrons in an atom. They're going to be the ones that participate in chemical reactions. And what we found was a easy way to figure out how many valence electrons an atom has is by looking at what column it's in the periodic table of elements. So that any element that's in the first column, like hydrogen, is going to have one valence electron. It's in the first column. Anything in the second column is going to have two valence electrons. And then you skip the ones in yellow there. So those are called the transition elements. We're not that interested in them in here. And then you've got columns 3, 4, 5, 6, 7, and 8. And those represent those number of outer electrons. Okay, so what's the point here? So let's look at an element that is in the first column of the periodic table of elements. So let's take a look at, for example, sodium. Okay, sodium's in the first column. It's going to have one valence electron. Now, in chemistry, there is a magic number that elements want to attain with their outermost electrons. And the number is 8. So if an atom can get 8 outer electrons, it would be very satisfied. It would have a low energy, and it really would not participate in any chemical reactions. So the ones that do that are in column 8. So that's going to be like helium and argon and krypton. So anything that's in column 8 is very unreactive. So that, like for example, if you have a helium balloon and then you light a match and you stick it to the helium, it's going to pop the balloon, but there's certainly not going to be an explosion when you do that. Now on the other hand, if you got this balloon over here that has hydrogen in it, and then you strike the match, it's going to blow up. Ever heard of the Hindenburg? That's what we're talking about. So hydrogen is very, very reactive, but on the other hand, things that are in the 8th column are not so reactive. So in chemical reactions, atoms are going to beg, borrow, and steal so that they get to this magic number of 8. So let's go back to sodium. Sodium's in column 1. It's got one outer electron, so it's got a choice. It could grab 7 electrons, but it's easier for sodium to get rid of 1 electron, and then it would think it's neon. If you look up neon, you'll see that neon is in that 8th column. And that's what it would think it would turn into. Now, it doesn't really turn into neon, but by getting rid of that extra electron, it's very, very satisfied. And it will give up that electron to anything. It doesn't really care. If you take a piece of sodium and you hold it in your hand, it's going to burn your hand because that sodium is going to start to react with the water in your palm. So let's see an example of this. So what I want you to do is I want you to go to the internet and find a video entitled Sodium and Water, and then pond in parentheses. So you're going to wish that you had watched that video. So go watch the video. Okay, did you watch the video? Okay, this is why I said in the previous segment that it's a bad combination to have sodium, water, and teenagers put together. So what happened was that the sodium reacted with the water, and it basically split the water into, it made sodium hydroxide, but it also released hydrogen into the air, and then the heat of the reaction set off the hydrogen, and that was the explosion that you saw. So anything, any of the elements that are in the first column of the periodic table are going to be very explosive. Okay? They're very, very reactive because every one of them is just trying to get rid of one electron. Now, let's take a look, on the other hand, at chlorine. So chlorine was used during World War I as a chemical weapon. And if you breathe chlorine gas, you're going to die, okay? Because chlorine is in column, you tell me. So where is chlorine in the periodic table? What column is it in? Column 7. And what did we say it wants? It's got 7 valence electrons and it wants 8. So it's going to beg, borrow, or steal an electron in order to do that. So if you breathe chlorine gas, it's going to take the electron from your lungs, and then your lungs are not going to be able to operate chemically the way they're supposed to, and then you die. So anything that's in the first column is very reactive. Things in the second column are reactive, but not as reactive as the first column. Things in column 7 are very reactive, and things that are in column 6 are also reactive, but not as reactive as column 7. So now let's take our sodium, which we know is very dangerous, and let's take our chlorine, which is very dangerous, and let's put them together and see what happens. Well, there would be a chemical reaction and some heat would be given off, but what's left over is going to be sodium chloride, table salt. Because what's going to happen is the sodium is going to say, take my electron. Chlorine is going to say, Santa Claus has come to town, and I cannot copyright that. That's from Paul Hewitt. But anyway, the chlorine is going to say, give me that electron. And so now sodium becomes ionized. So it's going to be positive. Chlorine is going to be ionized. It's going to be negative, and we know opposites attract. So we're going to make sodium chloride, which is the stuff that you put on your French fries. Now, don't worry if you're saying, oh my goodness, if I eat salt, I'm going to blow up or I won't be able to breathe. Well, remember that when you take an atom and you pull off one of those electrons, it no longer has the same chemical properties it did when it had the electron. So it's okay for there to be sodium ions in your body and chlorine ions in your body. So they have different chemical properties than what sodium or chlorine would have inside your body. All right, in our next segment, we are going to talk about how do you give energy to atoms. I'll see you then.